Okay, so some of you might have seen this breadth first search algorithm in a graph theory, data structures, or algorithm classes, but some of you might not have seen. So I'm going to make it like, I could go over this in detail so that everybody's on the same page. So if you have already come across it, it will be like a review of this algorithm. So it's very useful, it's a very classical graph theory algorithm to do traversal, and it's useful for different applications. So we'll see the algorithm in this in this module, and some very basic applications in this module. Then the later modules will come back and use this extensively in very important topics. So make sure you understand this algorithm very well. It's very easy to understand. Okay. All right. So it's called the breadth first search algorithm for graph traversal. Uh, all right. Okay, so we'll make use of an example to understand the working of this algorithm. So what we want to basically do is start from some vertex in the graph and check if we are able to visit all the vertices or visit all the vertices. So how are we going to traverse the graph and visit the vertices? So that's called breadth-wise. So in the sense that first we'll start with some vertex, and that's called the starting vertex. It's indicated with S in this pseudocode here. And we're going to use a queue as a data structure to assist with this process. So I initialize that queue with that vertex I'm going to start. So that's why I put the vertex ID 1 here. Now, so we're going to maintain one information as we traverse the vertices. It's called the level numbers of the vertices. So the level numbers of the level number for a vertex indicates how far is the vertex from the starting vertex. So to begin with, vertex 1 is a starting vertex, so its level number is 0. So the distance, the number of edges from 1 to itself is 0. You don't have to go through any other edge to come back to 1. So 1 from a vertex to itself, the distance is 0. So the level number for vertex 1 is 0 because that's also a starting vertex. Now to the other vertices in the graph, we don't know the shortest path yet. So we would like to visit the vertices on the shortest path from 1. So to begin with, we don't know the shortest path from 1 to the other vertices. So we say the level number, which indicates the distance from the starting vertex, is 0 is infinity for the other vertices. Okay, so those are some initializations we do, and that's also given the pseudocode. So the level number for the starting vertex to itself, level number of S is 0, and every other vertex it is infinity. And we also keep track of whether a vertex has been already visited or not as part of the breadth first search process. So in the graph, I indicate that with a color. So if the vertex is colored in yellow like this, that means the vertex has been visited. And if a vertex has not been visited, I do not color them. Now I indicate that using a Boolean variable in the Boolean array in the pseudocode. So I have visited array, and if a vertex is not visited, it is false. If a vertex is visited, that is true. So for the starting vertex S, it is true. For everything else, it is false. So those are the initialization things that you do. So you initialize the queue, enqueue, add vertex S to the queue, then set the level numbers of the vertices other than S to be infinity. For S, it is 0. Then the visited Boolean flag for the other vertices is false, and for the starting vertex, it is true. So with all these things, we can go through the iterations. So in each iteration, what we will do is we will dequeue the queue. So queue in data structures means it's like a grocery store queue. So you can add things to the queue. So that's called the enqueue operation. So that means if you want to join the queue in a grocery store, you have to join the end of the queue. You cannot go and join somewhere in the middle or at the beginning of the queue. So you have to join at the end of the queue. Then if the person checking out, the cashier or whoever you want to call it, calls, okay, next person in the queue on the line, then the person who is the first person in the queue will come out of the queue. So that's a dequeue operation. So Q is considered to be a last in first out model. That means the first in first out model. So the why is called the first in first out model, because the first person who joins the queue is the first person to come out of the queue, right? So it's a first in first out model. Stack operates in last in first out model, but a queue is first in first out. All right, so vertex 1 joins the queue, is in queue. So in the beginning of an iteration, you just dequeue the queue once. That means you remove the vertex that is in the front of the queue, which is vertex 1. So vertex 1 is dequeued, so the queue is temporarily empty. So you dequeue the queue. So the vertex that you dequeue from the front of the queue, let us indicate that as vertex u in the pseudocode. So you basically visit the neighbors of vertex u. Okay, so for every vertex v that's a neighbor of u, you do these things. If that neighbor has not been yet visited, so that visited of that v is false, do these three things. Increment the level number of that, set the level number of v, that neighbor v to be one more than the level number of the vertex u. That's one thing. Then visited of v is now made true because that vertex has been visited, and also nq, that q vertex to the q. And in addition to these three, we also need to label that edge uv as a tree edge, because that vertex v is visited for the first time, that is through this vertex u. So this edge uv should be called a tree edge. So let us apply these things here. So the neighbors of vertex 1 are 2, 3 and 7, and you can process them in any order, it doesn't matter. We'll follow the lower ID convention, so we'll process the neighbor 2 first. So the things that we do are mark it as being visited, so color it, then set its level number to be one more than the level number of vertex 1, so 1 more than 0 is 1, so replace the level number from infinity to 1, and then mark that edge between 1 and 2 as a tree edge. So I highlight the edge color with green to indicate that's a tree edge. So those are the things we do, and we also enqueue vertex 2 to the queue. So queue will be temporarily empty, as I said, when you dequeue the queue and take out vertex 1. So now you add vertex 2 to the queue, so vertex 2 now becomes part of the queue. Now do the same thing with vertex 3. So mark it as visited, so color it, set its level number to be one more than the level number of vertex 1, so 0 plus 1 is now 1, and then mark that edge as a tree edge between 1 and 3, and enqueue vertex 3 to the queue, so 3 now gets to the queue. So this is why I said in what order you process the neighbors depends on how you want to do it, but we'll follow the convention of going through the lower ID vertices. So 2 and 3 are done. Now vertex 7, again label the vertex as being, mark it as visited, label the edge as a tree edge, set its level number to be one more than the level number of vertex 1, and then add 7 to the queue. So that's the first iteration, that you visited the neighbors or explored the neighbors of vertex 1. So just repeat the process. So in the second iteration, dequeue the queue. So the vertex that is in the front of the queue is vertex 2. So that's the vertex whose neighborhood we are going to now explore. Now the vertex 2 has two neighbors 4 and 7, which are already visited. So if you look at the pseudocode, if visited of v is false, you do the things that we did before. If visited of v is true, that means you go to the else part and just label this edge as a cross edge. Okay. So 2 has 4 that is not yet visited, so I should take it back. So but 7 has been already visited. So this is what we do for 7. So the neighbor 7 has been already visited. So you mark the edge between 2 and 7 as a cross edge, so indicate with the dotted line. But neighbor 4 has not been yet visited, so that means this visited of 4 will be false. So do all these 4 things. That means you should color label vertex 4 to indicate that's been visited, label that edge, mark it as tree edge, and then set its level number to be one more than the level number of vertex 2, so that's going to be 1 plus 1, 2, and then add vertex 4 to the queue. So after 2 was removed from the front of the queue would have 3 and 7. Now vertex 4 is getting added to the queue, so it will be 3, 7, 4. That is what is vertex. That's what will be the queue. Any questions so far before we go to the iterations? Okay. Alright, so now the queue has 3, 7, 4. If you dequeue, 3 comes out of the queue. So now 3 has 2 neighbors that have to be explored in the sense that are the edges associated with them are not being yet classified, so you can deal like that. So even though 1 is a neighbor of 3, that edge has been already classified, so there's nothing that 3 has to do with 1 in this iteration. So it has 2 more edges that are not yet classified, and we'll go on the basis. Now that edge with 4 is a vertex that has been already visited, so visited of B will be true now, so just label that edge as a cross edge between 3 and 4. Now this edge has not been yet classified, and this vertex has not been yet visited. That's visited of 5 is false, so that means we will have to make it as visited, label that edge as a tree edge, and set it level number of 5 to be 1 more than the level number of 3, so that will be 2, and then add 5 to the queue, so it will be like 7, 4, 5. Okay, and then just repeat the same process for the other vertices. So the next thing to process is 7. Now you see for vertex 7, you have classified both the associated edges. One is tree edge, other is a cross edge. So there's nothing to do with vertex 7. So you can simply remove vertex 7 from the queue. Then vertex 4, you have to still classify these 2 edges. So this edge to vertex 5 is a vertex that has been already visited. So this edge is simply a cross edge. And this edge to 6 is going to become a tree edge because 6 has not been yet visited. So it's a tree edge. The vertex 6 level number will be 2 plus 1, 3. And then the vertex has been visited and will be also added to the queue. So exploring 4, removing 4 from the queue, and the queue will currently have 5. Now you add 6 to the queue. Then you go dequeue vertex 5, but so this edge and this edge has been already classified, but this edge to 6 has not been classified. But this should be what a cross edge because 6 has been already visited. And then the last iteration will be left with only 6, and all its edges are already classified, so there's nothing we need to do with 6. So dequeue 6 also. So the queue becomes empty. So this is how you now also can check. We started with some vertex, add the vertices to the queue and go through this process, and if by the time the queue becomes empty, if you have visited all the vertices in the graph, then we can say the entire graph is in one connected component. Means you can reach from any vertex to any other vertex. We say all the vertices are in one component. Now think about a graph like this. Okay, so if you start breadth first search from any of these 6 vertices A, B, C, D, E, F, you will be able to visit only those vertices. You will not be able to visit G, H, I or J if you start from any of these 6 vertices. So we say it's one instance of breadth first search. One instance means you start breadth first search from some vertex like this, go through all the iterations, and by the time the queue becomes empty, you check whether we have visited all the vertices. So that is one instance of breadth first search, starting from one vertex and the queue becoming empty ultimately. That's one instance. Now if you do that here, you start say from A, you will be able to sit only the other 5 vertices B, C, D, E, F, and the queue will become eventually empty. So G, H, I, J are yet to be visited. So we say A, B, C, D, E, F are now in one kind of component, and G, H, I, J are not in that component. They are in a different component. So how to visit them? So start breadth first search again. So that's the second instance, another instantiation of breadth first search. You can start from G, H, I or any vertex J. So as a convention, follow the lower ID vertex. So we can start from G, and with that you'll be able to visit all the other 3 vertices. So we say G, H, I, J are in one component. Okay, so here again I show the execution of breadth first search, and these are the numbers in the order in which they get into the queue. So so you need not keep track of things like this if that's too cumbersome or too much of work. As long as you keep track of what order the vertices enter the queue, that should be fine. Okay, so this is another way you can keep track of things. So I start with A, So that's the first vertex to get into the queue. And so from A, you can visit C, D, and E. So those are the neighbors of A. So mark them as being visited, and label those as tree edges. And the level number is one more than the level number of A. So that is 1 for each of them. And enqueue them to the queue. So you can enqueue them in alphabetical order. So C gets to the queue first, then D, then E. So A is already removed from the queue, so you need to keep track of that. So A is already removed from the queue, so you can strike or erase A. Then C, D, and E are the vertices in the queue. So C is to be explored now. Now C has two edges that are not yet classified, that is with D and F. So this edge with D will be called a cross edge because D has been already visited through A. So I indicated with the dotted line. Now F has not been visited yet, so this edge should be called a tree edge. The level number of F would be one more than the level number of C, which is 2, and then F is marked visited and F is also added to the queue. So the queue will now have C removed, D, F will be in the queue. Okay, so D is now to be dequeued. Now for D, both the associated edges with A and C are already classified, so there's nothing we can do with D. So we remove D from the queue and explore now the neighbors of E. Now for E, the edge to A is already classified, but the edge to F and B are not yet classified. But you see, F has been already visited to C, so this edge between E and F should be called a cross edge. Okay. Now B has not been yet visited, so that edge will become a tree edge, and the level number of B would be 1 plus the level number of E, so that's going to be 2, and B is being marked as visited, and B is added to the queue, so that's the 6th vertex to be added to the queue. So then you remove E from the queue, explore the neighbors of F. Now for F, both the edges with C and E already classified. The edge with B is not yet classified, but B has been already visited, so that should be classified as a cross edge. And that's all we can do with F. And ultimately then, so when F is gone, then B is the only vertex in the queue, so all its neighbors, the edges already visited. So done, the queue becomes empty eventually after we remove B. So you started breadth first search from A, and the queue eventually becomes empty, and you are still not yet visited G, H, I, J. So we say the vertices that were visited in one instance of breadth first search are in one component. And if there are some more vertices in the graph, okay, then it means the whole graph is not in one connected component. So if, unlike in this example, you started with one vertex, you're able to visit all the vertices, and by the time the queue becomes empty, there are no more vertices that are yet to be visited. So we say the whole graph is connected. So any vertex is reachable to any other vertex. But if it is like this, where there are some more vertices that are to be visited, and the queue already becomes empty in breadth first search, then we say the graph is not connected. So when a graph is not connected, we need to identify the different connected components of the graph. So we can use breadth first search for that purpose. So we can run multiple instances of breadth first search from each time from some starting vertex. So in this case, when you started from A, we are able to visit A, B, C, D, E, F. So these 6 vertices are in one component. And then similarly, you start say from G and identify the other component. So when you start from G, you can again start with, of course I use the same queue, so that's as a convention we can continue the numbering. So G is the 7th vertex to be enqueued, B was the 6th vertex, so G is now the 7th vertex. The level number of G is 0 because you're starting from G, and then you said H and J, it's 2 neighbors. Those vertices get level number 1, the edges become tree edge. So add H and J to the queue, and when G is removed from the queue, H is in the front of the queue, so its H to I is not yet classified, that becomes a tree edge, and the level number of I is 2. Then when H is gone, J is in the front of the queue, then the edge between j and I is not classified, that becomes a cross edge because I has been already visited through h. Then j is removed, I is the only vertex in the queue, we don't have anything else to do. So we say GHIJ or in another component. So this is an application of breadth first search. You can find the different components of a graph. Okay. Any question on breadth first search so far? Right, so let us continue and see some application of breadth first search. So one application, we see the connected components. The other is just, we can know the level numbers, as I said, indicates the distance from the starting vertex to any other vertex. So if you run breadth first search on this graph, these will be the level numbers. So well, these are the queues. So this is the order in which you visit them in the queue. But this is the level number. So let me mark here. So A is at level 0. B and E are said to be at level 1. Then C and F are said to be at level 2. Of course, everything is related to the starting vertex. So if you change the starting vertex, the level numbers will be different. Something happened. Let me redo it. So this is 0. That's 1. It's 2. And then we have 3. And 4. So this is called also the shortest path tree. Rooted at vertex A. So why I say it is rooted at vertex A, because that's the starting vertex. So the starting vertex of a tree. So why I call it tree edges? So if you put together the tree edges that we highlighted, you can find the shortest path tree. So in this example here also, I can do that. So let us put a separate slide. So shortest path tree. So this is the original graph given to us. So started from 1, and this is now the shortest path tree. So you can remove all the cross edges. So this indicates the shortest path tree starting from vertex 1. So if you just include only the tree edges, what you get is the shortest path tree. So the level numbers now indicate the path length. Okay, it's also called a shortest path tree is also called minimum edge tree. So both mean the same. Let me indicate that here. So shortest path is also the same as calling minimum edge path. Okay. So what's the minimum number of edges on the path between two vertices? That's the shortest path. So in this case, that can be found using the level numbers. Okay. So the shortest path from 1 to 7 is of length 1. The shortest path from 1 to 5 has 2 edges. That means it's length 2, level 2, and so on. Now, So that is something you can find. So I'm just enumerating a number of things you can do with breadth first search. So you can find the different components of a graph. We can find the shortest path tree starting from any particular vertex. So that will give you the distance from that vertex to every other vertex. That's the second thing we can find. And the third thing we can also find is check if the graph is bipartite or not. Okay. So a bipartite graph can also be called a two-colorable graph. So this is a terminology that people use in the graph theory community. So what I mean by two colorability of a graph. So if a graph is bipartite, right? So that means you're not going to have. Let me see if there's a bipartite graph here. Yes. So but let us take up this case here. So if this graph is, since it's bipartite, I can color the vertices in each set using a particular color. So these vertices are colored in light green, these vertices are colored in dark green, let us say. So for any edge, its two end vertices are in different color, because in a bipartite graph the edges are between only the two partitions. There's no edge between vertices in the same partition. So that's why we call a bipartite graph also as a two-colorable graph. So two-colorable graph means you're given only two colors, like in this case light green and dark green, and you have to color every edge in the graph in such a way its two end vertices are of different colors. And you can do that only if the graph is bipartite. So as a graph theory problem, people may give you a graph and ask you to find out is it two-colorable or not. So how would you find if a graph is two-colorable or not? Check if the graph is bipartite or not. If the graph is bipartite, then the graph is two-colorable. Otherwise, it is not two-colorable. So now the key thing we need to answer is, how would you check a graph is bipartite or not? So we know what a bipartite graph is, but you have not yet seen how to check whether a given graph is bipartite or not. And we can use the results of breadth first search that we got. So let us do that now. So if you run breadth first search on this graph, okay, so if you do that quickly, start from vertex. You can start from any vertex. You can start from A as a convention, the lower alphabet or lower ID. Then A gets gets level number 0. Its two neighbors B and D are at level 1. And the dark color edge, the brown edge, is my tree edge in this case. Okay. So A and B have the tree edge. A, B and AD edges have tree edge. So now you have B and D in the queue. So you can keep track of the queue if you want to. So initially A was in the queue, so now the queue has B and D. So now you visit the neighbors of B, that's going to be C and E. Both are not yet visited. So you can label those edges as tree edges to C and E. And the level numbers of C and E will be one more than the level number of B, so that will be 2 for each of them, and add C and E to the queue. So now B is gone from the queue. D is the vertex to be explored. Now for D, this edge to A is already classified, but this edge to E is not yet classified. But since E has been already visited, this edge to E should be marked as a cross edge. So D is also gone. Then C is in the front of the queue. Then explore the neighbors of C. Now this edge is already classified. This edge to F is not classified, and F has not been visited either. So we have to label this edge as a tree edge. Add F to the queue. Of course, C is now removed from the queue. So add F to the queue. Set the level number of F to be one more than the level number of C. That is going to be 2 plus 1, 3. And mark F has been visited. So now you have E and F. E is the front of the queue, so they'll remove E, and the edge to F has not been classified, but F has been already visited, so this edge becomes a cross edge. So that is how you run breadth first search and identify the level numbers of the vertices from the starting vertex, and then the tree edges and cross edges. So now how to decide whether this graph is bipartite or not. So the rule for bipartite is this. A graph is, after you do breadth first search on the graph is said to be two colorable if there are no cross edges between vertices at the same level. So check in this graph. there are two cross edges, but each of these cross edges are between vertices at different levels. So this cross edge DE is between vertices at levels 1 and 2. This cross edge EF is between vertices at levels 2 and 3. So the criteria requirement is there should not be any cross edge between vertices at the same level, right? And we don't have that here. There are no cross edges between vertices at the same level. There are cross edges, but they are between vertices at different levels. That is okay. There should not be even one cross edge between vertices at the same level. If there's at least one such cross edge between vertices at the same level, the whole graph is said to be not two colorable, or it is not bipartite. But in this case we don't have that. So that means this graph is bipartite, that is, it is two colorable. So once we decide that it is bipartite, we need to now find what are the two partitions of the graph such that we can color each partition with the two different colors. So how to identify the two partitions? Again, the rule is very simple. Use the level numbers of the vertices. So the vertices, say, in the odd levels are in one partition, and the vertices in the even levels are in the other partition. So applying that rule, A, C and E have even level numbers. 0 can be considered as even. So A, C and E are colored in, say, yellow, and then B, D, F are in a different part, or having odd level numbers. So they'll be in the other partition. And you can cross check now. Every edge in this graph is between vertices with two different colors. So A, B different color, B, C, C, F, E, F, B, E, A, D, D, E. So this is a bipartite graph. So even though it doesn't look like a bipartite graph, now if you draw it like this as a two set of partitions, A, then what, C, E, and so it coming out capital, that's okay, then B, D, F. So now if you just redraw the edges between, so it's A, B, then there's another edge between A and D, then BC, there's an edge, that's this CB, then you have DE, then you have CF, then you have DE, then EF. So you see all the edges are between vertices in different partitions. They are not between vertices in the same partition. Okay, so this is a bipartite graph. Now, as a complete package question, what I could do in exam is this. I could give you a graph like this or any graph similar to this and ask you to check if the graph is bipartite or not. And it will be bipartite, but you have to do all this work and show it is bipartite. Okay. Then once you identify the two partitions of the graph, I'll ask you to call the larger partition as the vertex set and the smaller partition as the group set. Okay. So in this case both have the same size. So in case of a tie, you can call one of the partitions as a vertex set and the other as a group set. But in case if the partitions have different number of vertices, so for example, if one partition has 4 vertices and the other partition has 3 vertices, if there are 7 vertices in the graph and it comes out like 4 in one partition and 3 in the other, or 5 in one, 2 in the other, it could be possible, depends on the graph and the edges. Then consider the partition with more vertices as the vertex set and the partition with the smallest vertices, fewer vertices, as the group set. And then do this analysis of vertex position and group projection. Once you identify such a partitioning, then you can come up with the adjacency matrix of that bipartite graph and do all this matrix multiplication process to get the vertex projection and group projection and come up with these matrices. So that could be a larger complete question. Okay. So you need to run breadth first search, identify the bipartite graph at the two partitions, and then come up with the vertex projection, group projection. Now let us do a case of the graph being not two colorable. So how you find out if a given graph is two colorable or not. So one more case. So let us use a simple example here of A, B, D and E. So start breadth first search from A. So A is in the queue and visit its neighbors B, D and E. So all the three edges or tree edges, label them as being visited, and then the level numbers of B, D and E all will be 1 because they all can be visited from A. So now you add B, D, E to the queue. So B and so B is the vertex that comes out of the queue now. Now B has this edge to E that has been not yet visited or classified. So we call that as a cross edge because E is already visited. So then remove B from the queue. Then D has this edge to E that is not yet classified, but it's also a cross edge because E is already visited. So E is removed from the queue and we don't have anything to do with E. So now if you explore the cross edges here, there are two cross edges and both of them are between vertices at the same level. So if you go back to the criteria, there should not be any cross edge between vertices at the same level, and there are two cross edges. So even one cross edge is sufficient to rule out the graph is not bipartite. So this graph is not bipartite because there's at least one cross edge between vertices at the same level. Now if you think about this, and if we can try to make sense, why they cannot be cross edges at the same level. So you see here, you have, if the two vertices are the same level, then they have a common what we call ancestor from which they have this tree edge. So A and D. So D has a tree edge to A, E has a tree edge to A, and A is at an earlier level. So it's like a parent node. So A, and then you have child node D and E. So both D and E have the same color because they came from A, this ancestors. So they have tree edge to A. So if D and E now have an edge between them, it's not possible to color the D and E with different colors because they both came from A and they are just one level away from A. So they have to be of the same color. Okay, so that's why we cannot color D and E with two different colors. That the graph is not two colorable. So I have one more example that you can practice to check if the graph is two colorable. So the process is start from some vertex. You can start from any vertex, need not be always A. As a practice, you can start from some other vertex and see. So like in this case, you can start from A as a convention and then you explore the neighbors and so on. Now if the question is a smaller question like this, so if I just ask you to given a graph check if it's bipartite or not, okay, and you see you start from A, you encounter B, C, D, E as the vertices that can be visited, so all those are tree edges, and then you start from B, explore the neighbors of B, and you see they have a edge to D. That's a cross edge because D has been already visited through A, and both B and D are in the same level. So you can stop right there and say this is not a bipartite graph. So for smaller questions like that, given a graph check if it's bipartite or not, the moment you encounter one cross edge between vertices at the same level, you can stop and say the graph is not bipartite. So you do the entire breadth first search only if everything goes fine as you do the iterations. Okay, so like here, this is a different graph compared to this. So if you do breadth first search on this, you have A has a tree edge to B and C and E. Then you explore the neighbors of B, you have a tree edge to F and D. Explore the neighbors of C, you have a tree edge to G. Then this edge between G and E will be called a cross edge, but that cross edge is between vertices at two different levels. So this graph is actually bipartite because there's only one cross edge and that's between two different levels. So the two partitions are going to be based on the level numbers. The ones that are at the odd level are in one partition, the ones at the even level are in the other partition. So this has like you see A, let me draw here somewhere, A, D, F and G are in one or even level, and B, C and E are in odd level numbers. So these are the two partitions. And so like in this case we can use the larger set of vertices as the vertex set and then the smaller set of vertices as the group set, and then find the group projection and vertex projection, okay, as I said before. Okay, any questions so far before we have some time? Any question? Okay, let me save this.